In this video, we cover another example of an optimization problem where we use the second partials test to find the maxima or minima of a function of two variables. In this case, we want to find the dimensions of a rectangular package of largest volume, such as the sum of the perimeters of the two cross-sections cannot exceed 144 inches. This is like a typical packing problem. If you go to the post office, there are restrictions on the dimensions of the packages that you can send. So in this case, we want to find the largest volume so that the sum of the two perimeters of the cross sections cannot exceed 144. We're going to start off with I like to draw pictures whenever possible. We have a rectangular package. And it has three dimensions. We could label them X for the length, Y for the width, and Z for the height. And what we want to do is we want to maximize the volume. So that's going to be our primary equation. We're going to maximize volume. Now the volume of a rectangular solid is the length times the width times the height, and if we are labeling the dimensions x, y, and z, the volume is going to be x times y times z. Now we want to we want to be able to find a formula for volume with just a function of two variables, so we can use the second partials test. But right now this is a function of three variables, so we need to use the other information given to come up with a secondary equation that we can substitute in. Now we do know that the sum of the perimeters of the two cross sections cannot exceed 144. To maximize this volume, we want it to be equal to the greatest. We want it to equal 144. So let's look at what that means. Two cross sections. Well, if you're looking at a cross section of this rectangular solid, one cross section would be going in this way. This perimeter of that cross section, you can label the sides. If this side is x, then this side is also x. If this height is z, then the height is z here, and the height is z there. So that one perimeter would be found by adding x plus z plus x plus z. That's two x's plus two z's. So we can say 2x plus 2z, and we're going to add that to the other perimeter of another cross section. Let's look at the cross section looking at it from this way. This perimeter, the perimeter of this cross section, if we know the sides, if this side is y, then this is also y, and we know the heights are both z. So the perimeter of that cross section would be y plus z plus y plus z, or 2y plus 2z. That's the sum of the perimeters. If you combine like terms there, you can write this as 2x plus 2y plus 4z. We want that to equal 144. We can call this P1 for the first perimeter and P2 for the second perimeter. That's the sum of the cross sections, sum of the perimeters of the two cross sections. We want that to equal 144. Now notice again we have our volume, which is a function of three variables, and this equation has three variables. We can substitute. This is our secondary equation. If we solve this for z by subtracting 2x and 2y from both sides and then dividing by 4, we get that the z is equal to 144 minus 2x minus 2y, all divided by 4. That's going to give us 36 minus half x minus 1 half y. Again, I subtract 2x and 2y from both sides and divide by 4. When you simplify it, you get this equation for z, and then we're going to plug it into this formula that we're trying to maximize. We want to maximize the volume. So this equation, we get volume equals x times y times z, but we're going to replace z in this equation with what z equals in that secondary equation. Alright, so now we have a formula for volume, which is a function of two variables. We want to use the second partials test to determine um, if there's a relative maximum for this volume. We want to find the critical points, and we do that by setting the first partial is equal to 0. Before taking the first partials, I'm going to go ahead and distribute that xy so that we get volume equals 36xy minus 1/2 x squared y minus 1/2 xy squared. Now we can take the partial derivative of this with respect to x and with respect to y. The partial derivative of this with respect to x is going to be where you treat x as a variable and y as a constant. We get 36y minus 1/2 x squared minus xy. Okay, oops, excuse me. All right, let's try that again. We're going to take the partial derivative with respect to x, treating x as a variable. This is going to be 36y. The derivative of 1/2 x squared would be minus x times that constant y, times the derivative of this 1/2 x is minus 1/2 times your y squared. We're going to set that equal to 0. Now we want to take the partial derivative of this with respect to y. Treat y as a variable, x as a constant. You get 36x minus the derivative of this constant times y is this constant, 1/2 x squared. And then the derivative of this, it's 2 times 1/2 x. That's going to be minus xy. Again, we want to find out where that is equal to 0. Here we have a system of equations, two equations, two unknowns. We cannot use a matrix here yet because it's not a system of linear equations. We can do some factoring here. You can factor out, since these have a common factor of y and these have a common factor of x, you can factor out that y in the first and the x in the second to simplify this equation. If you factor out the y, you get 36 minus x minus 1/2 y. And then if you factor out the x from the partial with respect to y, you get x times 36 minus 1/2 x minus y. Again, since these are set equal to 0, if you set each of these equal to 0, y equals 0, and x equals 0, are solutions, they're critical points, but we can eliminate those as possible values that would maximize the volume. If the x or the length was 0, or the y was 0, the width was 0, the volume would be 0. So that certainly would not maximize the volume. So even though y equals 0 and x equals 0, that would be a critical point that would give you a volume of 0. So we can eliminate that choice. So let's look at the possibilities where this system of equations is equal to 0. Okay, so here we have the system of equations where we've eliminated that possible critical point of x equals 0 and y equals 0. So we want to find out where this is equal to 0 and this is equal to 0. This is a system of equations. You can, again, use the elimination method, substitution method, or you can use the matrix method. By rearranging this, you get negative x minus 1/2 y would equal negative 36, and then negative 1/2 x minus y would equal negative 36. Since you can write it in this form, you can use a calculator and the matrix method to solve the system of equations. To solve the system, you want to go to edit the matrix, and you want to enter the values, negative 1, negative 1/2, negative 36, negative 1/2, negative 1, and negative 36. So you're going to plug those into the matrix, then press second quit to get out of the edit mode. Second quit, then go back to the second matrix. You're going to go to the math menu and scroll down until you see that command for RREF. Oops, wrong one. Second. Go to the math, scroll down. Okay, reduce row echelon form of the matrix that we edited to find the solution to the system of equations. In this case, the matrix, when you reduce it, you get 1, 0, 24 and 0, 1, 24. So that means x is equal to 24 and y is equal to 24. So we can go back to our original formula. In fact, that we were trying to maximize the volume was the length times width times height, and we labeled the length as x, the width as y, and then our height was z. And then we used the equation where we solved for z to find the volume was x times y times 36 minus 1/2 x minus 1/2 y. Now if you plug this x and y back into this function, so evaluate the volume when x is 24 and y is 24, you get, this is 24 times 24, and then if you put that x and y, 24 and 24 into here, you get 12. So, and that volume can be found by multiplying those together, 6,912, and since those were measured in inches, the perimeter was given in inches, this volume is in cubic inches. So the dimensions that we're looking for, what size box is going to give us the greatest volume if the sum of the perimeters of the two cross sections cannot exceed 144. The dimensions are going to be 24 inches for a length, 24 inches for a width, and then 12 inches for a height. That's going to be the dimensions of the box that will hold the greatest volume, given those restrictions. And again, we use the partial derivatives to find the critical points. Now, I didn't go through and confirm that this is a maxima or a minima, but you can certainly do that by finding d, which would be the value of vxx at that critical point, vyy minus the vxy quantity squared, and you'll find out that that is greater than 0. This would be less than 0, which would confirm that you have a relative maximum.